Welcome to Basic Electronics Module 1. In this video, initially let us see the configurations of operational amplifier. There are three basic configurations for operational voltage amplifiers. So these are the three basic configurations for operational amplifiers. The first one, this is the inverting amplifier. The name itself says the input is applied to the inverting input terminal. The signal applied to the inverting input terminal, it will get amplified. Let us see the circuit. This is a symbol of the operational amplifier: inverting input terminal, non-inverting input terminal. To the inverting input terminal, we are applying the input. We are applying the input with respect to the ground, with respect to the common terminal. We apply the input. Suppose if this is the input voltage waveform, which is applied to the inverting input terminal through a resistance, here it is written as Rn. Non-inverting input terminal is grounded through a resistance Rn. Here there is a feedback. Some portion of the output is fed back as the input through a feedback resistance Rf. As the input is applied to the inverting input terminal, the output what we can expect is the amplified but inverted. This was the input. This is the input. The output waveform looks like this. So whatever you apply at the input terminal, it gets inverted and also it gets amplified. So remember, inverting amplifier, input is applied always to the inverting input terminal. The non-inverting terminal is grounded, feedback is applied through a feedback resistance. Non-inverting amplifier, the name itself says non-inverting. So input is applied, the input is applied to the non-inverting terminal through a resistance Rn. So that's all the difference between the inverting and the non-inverting. But see the inverting terminal as usual Rn. In the inverting terminal, in the inverting amplifier, we applied the input to the inverting input terminal through Rn. But here see the inverting terminal is grounded. Inverting input terminal is grounded because it is non-inverting amplifier. But feedback is applied to the same terminal. In the non-inverting input amplifier, to the non-inverting input terminal, we apply the input with respect to the ground. Inverting input terminal is grounded, and as usual, there is feedback. If this circuit is confusing for you, you can write the circuit which is similar to the inverting amplifier. Usually we write the operational amplifier like symbol like this, always inverting terminal at the top, non-inverting terminal at the bottom. So earlier there was a resistor here Rn and there was a feedback here output. Here in the inverting amplifier, we applied the input here. Now we are talking about the non-inverting amplifier, so ground this, but apply the input to the non-inverting terminal. Apply the input to the non-inverting terminal. Apply the input here. Apply the input to the non-inverting terminal. So this circuit is same as this circuit. So whichever you feel comfortable, you follow it. Usually I follow always to write the op-amp like this, always upper inverting terminal, bottom non-inverting terminal. This is my convention, always I follow. So I will go with this circuit. If you are good enough, you can write this circuit also, no issue. Here inverting, non-inverting, but here you should remember in the non-inverting amplifier, to the non-inverting terminal we should apply the input. Inverting terminal is grounded and feedback is same. Here you can observe, here there is no dot, that means there is no connection. Where there is a dot, there is a node, there is a junction, then there will be a connection. So Rn is connected to the inverting terminal. Rn is not connected to the non-inverting terminal. So here there is no connection here. Otherwise you follow this circuit. So after inverting and non-inverting amplifier, let us move on to the differential amplifier. The name itself says it amplifies the difference between the two input signals. What are those two input signals? Where they are applied. One of the input signal is applied to the inverting input terminal through a resistance Rn. The another input is applied to the non-inverting terminal through one more resistance Rn. So here there is a feedback, which is feedback resistor, which is grounded here. Then as usual there is a feedback to the inverting terminal through the feedback resistance. So this is a differential amplifier configuration where we apply the two inputs here. This input with respect to ground. Here also we apply the input with respect to the ground. Here in the inverting we apply to the inverting terminal, here non-inverting terminal. Let us see some of the applications of operational amplifiers. Very simple application is the voltage follower. The name itself says the output voltage follows the input. The output voltage follows the input, voltage follower. Or you can remember this as unity gain amplifier. Unity gain amplifier. Unity gain amplifier. That means gain is 1. The unity gain amplifier, the gain is 1. If the gain is 1, then only the output follows the input. Let us see the circuit. As usual, we will write the symbol inverting terminal, non-inverting terminal. We apply the input to the non-inverting terminal because the output should follow the input. There should not be any phase difference. So we apply the input to the non-inverting terminal, that is always with respect to the ground. And here the feedback, the 100% of the output, 100% of the output is fed back to the input. Usually in the previous circuits we have seen there was a feedback resistance, but in the voltage follower 100% of the output is fed back to the input. So very simple circuit, very simple circuit. Draw the operational amplifier, inverting terminal, non-inverting terminal. Here apply the input, then 100% of the output is fed back to the inverting terminal. That's all the circuit. Then you may ask, what is this? So this is a ground line, common rail. If the output follows the input, it is same. Output is same as the input. Then what is the use? Then why we call it as, where we use this, why it is called as unity gain amplifier. Gain is nothing but output by input, V out by V in, output by input. They are same. So you will get 1. So it is a unity gain amplifier. If output follows the input, then where we can use this voltage follower? We can use the voltage follower as a buffer. I hope you know the meaning of a buffer. It just acts as a storage. Nothing it will change. So temporary storage we can use. For example, if the computer, you use a computer to print a document, you will give a command to print, but printer cannot print at the speed of the computer. What it will do, it will save the document in the buffer. So it will go on printing, but in the computer you can do some other operation also. There the buffers come into picture. Here we can use this voltage follower as a buffer. So voltage gain is 1. So it is having very high input resistance, One more mistake here is, this is very low output resistance. I don't know why VTU has selected this as a prescribed textbook, which consists of lot of mistakes. So in your notes, in your downloaded notes or textbook or PPT, you should make all these changes. The result is an amplifier that has a voltage gain of 1, a very high input resistance and a very low output resistance. This stage is often referred to as a buffer. Whenever you hear voltage follower, definitely you should remember the application as a buffer, because the gain is 1, and is used for matching high impedance circuit to a low impedance circuit. So the two applications are, it can be used as a buffer and an impedance matching network. The second application, you can use the operational amplifier as a differentiator. The differentiator produces an output voltage that is equivalent to the rate of change of its input. A differentiator produces an output voltage that is equivalent to the rate of change of its input. Let us say the circuit. This is a circuit diagram. As usual, always we apply the input to the inverting terminal only. Here the input is applied to the inverting terminal through a capacitor, and there is a feedback through a feedback resistance R. Non-inverting terminal is grounded. That's it. An operational amplifier, one capacitor, one resistor. Input is applied through the capacitor, feedback is applied through a feedback resistance. Non-inverting terminal is grounded. So what you should be careful is whatever the output you will get here, it will be inverted form of the original output, because the input is applied to the inverting terminal. And also, you know, in the differentiator, if the input voltage remains constant, the output also remains constant. That is 0. You know, the differentiation of a constant value is 0. Now, for simplicity, let us consider a square waveform. Square waveform as the input voltage that is applied at the input. This is the voltage waveform that is applied at the input of this operational amplifier. So usually what we understand, the constant differentiation of a constant is 0. Differentiation of constant is 0. Here the voltage is constant, here constant, here constant, here constant. But here the voltage is increasing from negative value to the positive value. Here the voltage is decreasing from positive to negative. Here from negative to positive. Here are the voltage changes. Otherwise it is constant. The differentiation of a constant value is 0. In the output voltage waveform you can see 0, 0, 0. Because the differentiation of a constant is 0. Now, here the voltage changes from negative, here the voltage changes from 0 to negative, 0 to negative. Now, here we will get a spike, a negative spike. What we understand is negative spike. Here it is changing, voltage changing from negative to positive, so positive spike. Here negative spike, here positive spike, something like this. But this input is applied to the inverting terminal, so the output here is, here we had written a negative pulse, but here a positive going pulse. Here we have written a positive pulse but a negative pulse, because it gets inverted. Here I have written negative, but actually you will get positive pulse. Here I have written positive, so you will get negative pulse. A train of pulses you will get. Notice how the square wave input is converted to a train of short duration pulses at the output. So you should remember the output is inverted. I hope you have understood. Integrators. Observe the circuit. Earlier in the differentiator we applied the input through a capacitor, but here feedback is applied through a capacitor, input is applied through a resistance. As usual, non-inverting terminal is grounded. Here also the output will be inverted form of the input, inverted form of the integral of the input. I hope you know the English meaning of the integration. It is summation. If you consider this as an input waveform, a square waveform or rectangular waveform you can consider. Here we consider the area, here it is the area, negative area. Here if you go on adding, definitely the area increasing. Then the area is positive. Now if you go along that time axis, the area increases positively. Then the area here, it increases in the negative. Here the area increases. So you should add the area. Under that curve. So what usually we expect, here it is negative area, here it is negative area. Here this is the negative area. So if you add, you should get a negative ramp. Negative going ramp. What we expect is we should get a negative ramp. But as the input is applied to the inverting terminal, the output is a positive going ramp up to this positive going ramp. So after that, the area is positive. Go on adding this area. Actually, we expect a positive going ramp. But what we are getting? We are getting a negative ramp because the input is applied to the inverting input terminal. Again, the negative area, go on adding, but here positive ramp, negative ramp. So in the integrator, if you apply a square waveform as an input, you will get a triangular waveform as the output. Whenever you want to convert the signal from square wave to the triangular wave, you can go for the integration. You can see the integrator circuit and the input and the output waveforms. Then the comparator. Comparator is a circuit which is used to compare two values. Here we can compare two values. The voltage, let us say the voltage applied at V1 is 2 volts. Let us say the voltage applied at V2 is 3 volts. See the circuit, very simple, no feedback, nothing. So apply 2 volts to V1, 3 volts to the non-inverting terminal. So what we expect here? As you know, we will recall, here we apply plus 15 volts, here we apply minus 15 volts, plus VSS and minus VSS. That means the output can swing only between plus 15 and minus 15. The maximum swing is plus 15 and minus 15. Whatever may be the gain may be 1000 or 2000 or 10,000 voltage gain, but the output cannot go beyond plus 15 and less than minus 15. So it is a saturation output. It is a saturable property of the operational amplifier. So it cannot go beyond plus 15 volts. It cannot go less than minus 15 volts. Now let us come to the comparison 2 volts and 3 volts. You know that 3 is greater than 2. You know that 3 is greater than 2. 3 is applied. 3 volts is applied to the non-inverting input, that is positive. So positive supply voltage is plus 15 volts. So you can expect a plus 15 volts. Plus 15 volts at the output. Plus 15 volts at the output. Suppose, let us change the inputs. Instead of 2 volts at the input, let us change the inputs. Here I will apply 2 volts. Here I apply 1 volt. 2 volts at the inverting terminal, 1 volt at the non-inverting terminal. Here is plus 15 volts. Here is minus 15 volts. As you know, 2 volts is greater than 1 volt. 2 volts is applied to the inverting terminal. So output voltage you will get minus 15 volts. Minus 15 volts. Now let us apply the input voltage. This input voltage at V1. This input voltage at V1. And a sinusoidal signal at V2. Now we want to compare these two. Which is greater, which is less. Comparison means the result is always greater or lesser. So which is greater or which is smaller. So this is input voltage applied at V1. This is input voltage applied at V2. Now we need to compare which is greater, which is greater. So for that I will write the input voltage applied at V1 here itself. Now you can see this area, that is the input voltage applied at V2 is greater than here. The input voltage applied at V2 is greater than the voltage applied at V1. Here this area, that is the voltage applied at V2 here is greater than the voltage at V1. Similarly here, we'll talk about the signal here and here. The voltage applied at V2 is smaller than the voltage applied at V1, or voltage applied at V1 is greater than the voltage applied at V2 here. Then how to write the output? Now here in this region, the input applied at the V1 is greater. This is greater here. If you still not understanding, I will write here, this is plus 5 volts. The input voltage I will write it as 2 volts. Let us say this is 2 volts. Here this is minus 5 volts. Voltage at V1 is always 2 volts because this is DC. But voltage applied at the V2, the signal applied at the V2 is a sinusoidal signal. Always it starts from 0, goes to the peak plus 5 volts, comes back to 0, goes back to minus 5 volts, then 0, plus 5, 0, it goes on changing. Now from 0 to 2 volts, voltage applied at V2 is smaller than the voltage applied at V1, because see the red line, this is the voltage applied at the V1. Now here it is greater. So here if it is greater, the voltage applied at the inverting terminal is greater, you will get minus 15 volts, minus Vs. So here you are getting minus Vs, very small segment. Then coming back to this region, observe carefully this region. This is the voltage applied at V2 and this is greater than the voltage applied at the V1. Just you can make out by just observing. So this is the voltage which is greater than the voltage applied at V1. This is the voltage applied at the non-inverting input terminal. So the output voltage will be plus Vs. So for that region it is plus Vs. It's plus Vs. And after that, this region is smaller than the voltage applied at V1. V1 is greater. V1 is applied at the inverting terminal. So the output voltage will be minus Vs. So you can observe minus Vs. For this region it is minus Vs. And after that, here come back to this area. This is the voltage applied at V2 which is greater than V1. V2 is greater than V1, so output voltage will be positive. So it repeats. So from this what we can make out here is, so in this region, that is minus Vs, so the voltage applied at V1 will be greater than V2. V1 is greater than V2, so we are getting minus Vs. So in this region and in this region, we are getting plus 15 volts or plus Vs. That means V2 is greater than V1. V2 is greater than V1. In simple words, whenever V1 is greater than V2, the output voltage will be minus Vs. Whenever V2 is greater than V1, the output voltage will be plus Vs. That's it. If you remember these two, you can write the waveform. Then summing amplifier, or it can also be called as an adder. So it adds two signals, two voltages. This circuit produces an output that is the sum of its two input voltages. So the circuit is the operational amplifier. Non-inverting terminal is grounded as usual. To the inverting terminal, instead of one signal, now we are applying here two signals through the resistance RR. Here one signal, here one signal. No rule that you should apply two signals, minimum two signals, because we want to add, so minimum two voltages we need. More than two also you can apply. You can connect one more resistor here, you can apply V1, V2, V3 or V1, V2, V3, V4, etc. For simplicity or for first semester this is sufficient. So let us consider two input voltages V1 and V2 applied through the resistances R to the inverting terminal, and there is a feedback from the output to the inverting terminal through a feedback resistance R. Here they have selected all the resistance values as the same value. Now we will go for the simple example. 1 volt we will apply to V1, 2 volt we will apply at V2. It is adder circuit or a summing amplifier. Then what we can expect at the output? It adds this 2 volts and 1 volt, so we expect 3 volts. But remember, this input is applied to the inverting input terminal. So the output voltage will be minus 3 volts. So this minus because the input voltage is applied to the inverting terminal. So the equation here given is Vout is equal to minus of V1 plus V2. Vout is equal to minus of V1 plus V2, because this, why this negative sign? Because the input is applied to the inverting input terminal. If you apply still more voltages V3, V4, etc., Vout is equal to minus of V1 plus V2 plus V3 plus V4, etc. Now instead of that constant DC voltages, now let us try with the AC voltage waveforms. Let us assume the sinusoidal signal is applied at the V1 and at V2 there is a square waveform applied. It is an adder circuit. Definitely these two waveforms should add. These two waveforms should add. How this will get add? Something like this. The sinusoidal waveform gets added to this. But the input voltage is applied to the inverting terminal, so this should get inverted. Just imagine this is getting inverted here. Just invert it. Just invert this, you will get the proper output. This is the output that we will get for the summing amplifier. So we can understand like this, but while writing we must write like this. So the output waveform is on the square waveform. This sinusoidal waveform gets added. This is called as a mixing of two input signals to produce an output voltage that is the sum of these two. Let's imagine, see here, this is going to the positive peak, here it is going to the positive peak, it gets inverted, so it is going in the negative direction now. Here it is going negative here, but here it is going positive. Here it is going positive, increasing here, it is increasing, here it is decreasing, because it is the input is applied to the inverting terminal. These are the applications of the operational amplifier. Thank you.